kusenko letter file. It's a pleasure to be here in Stockholm again. What I'm going to talk about is a search for a dark matter candidate, which I find both theoretically plausible and well motivated from a statistical point of view. I will tell you about these motivations, and then I'll tell you how a particle physicist has converted into an X-ray astronomer. I actually got observing time on the Suzaku telescope, and I'll tell you what I'm doing with it. The dark matter problem requires one more particle, and if you look at the standard model, none of the standard model particles can do the job, except the right-handed neutrinos, which we introduced for another reason, to explain the ordinary neutrino masses. If one of the Majorana masses is below the electroweak scale, that particle can be dark matter. So I'll discuss the way it arises from the seesaw mechanism, and there's many mechanisms. Sometimes it needs adjustment. I will then discuss production of sterile neutrinos or right-handed neutrinos in the early universe, and the astrophysical hints coming from the supernova and realization that this may actually be the right story. And I'll discuss some bounds and the search for this form of dark matter with an X-ray telescope that we're conducting with Mike Lowenstein and Peter German. Sterile neutrinos were invented very early on in the game because it's very difficult to give ordinary neutrino masses otherwise. The name was coined by Bruno Pontecorvo in the seminal paper where he discussed lepton number violation, neutrino double beta decay, mutant gamma, vacuum neutrino slave. Well, basically, the neutrino physics program for the next 40 years. That's a 4-page paper. Kind of impressive. In this paper, this is a picture of Pontecorvo scuba diving and spear fishing about 50 kilometers from the place where I grew up. And he calls them sterile because they are inert from the point of view of electron interactions. Now, how do they come about? If you look at the active neutrinos, they of course are sp2 doublets. They cannot acquire a hard mass in the Lagrangian, nor is it easy to give them mass to the Higgs mechanism. What you would need is some sp2 singlet to couple the left-handed doublet to the Higgs via Yukawa interactions. There are other ways, perhaps, but the Majorana mass for the left-handed neutrinos is something that would have to be an sp2 triplet, and it is not easy to design a model to do this, although people have designed models. So what I'm going to do, I'm going to just set that mass to 0. And what remains is the Dirac mass term for neutrinos, which comes from this Yukawa interaction. And one more possible mass term, which is Majorana mass, that involves right-handed fields alone. We don't know how many right-handed fields there are, but it seems that you need at least 2 to explain the observed neutrino spectrum, but there's no anomaly constraint or any other constraint that will tell you how many right-handed spaces. So you end up with this matrix where there is a Dirac mass term and Majorana mass term, and the question is, what do you choose for the Majorana mass term? Okay? So here there is conventional wisdom, and I will try to question whether the reasons for the conventional wisdom are good enough. The conventional wisdom is to take this Majorana mass to be very large and to shove all these right-handed fields beyond observability. If this Majorana mass, or at least one of them, is below the electroweak scale, then you can still explain all the observed neutrino masses. Plus, you get a dark matter candidate, plus this particle would be emitted asymmetrically from a supernova, and which gives some explanation to some puzzles which otherwise are difficult to explain. So by diagonalizing that matrix, one gets mass eigenstates with masses Dirac mass squared over M. And there is a beautiful way to explain the smallest of neutrino masses, even if this Yukawa coupling is of order 1. And that way is to take mass to be large enough so that the Yukawa is of order 1, the heat expectation value is electroweak scale, but this huge mass in the denominator suppresses the neutrino masses. So this works very well if Yukawa is over the 1. Do we know whether Yukawa is over the 1 or not? Well, for all the observed fermions, Yukawas are much smaller than 1, with the exception of the upward. The electron Yukawa coupling is 10 to the minus 5, 10 to the minus 6. So, do we have a good motivation for thinking that neutrino Yukawa couplings should be over the 1? Well, it depends on the underlying fundamental model of neutrino physics. If Yukawa couplings come from string theory, where they are intersection numbers of some manifolds, then naturally they are over the 1. However, if neutrino masses come from string theory, where they are the overlaps of wave functions of fermions located on different d branes, then these overlaps are naturally exponentially suppressed. And so Yukawas much smaller than 1 are natural. Notice that the premise in both assertions is the string theory. In the absence of the fundamental theory of the Yukawa couplings, we don't know which of these two possibilities is preferred, even from just purely theoretical point of view. Well, maybe cosmology can give us a clue. If we have very heavy right-handed Majorana states, they can decay into the Higgs and the light neutrinos, and in these decays, using the CP violation from the neutrino mass matrix, one can produce the lepton asymmetry, which is converted to baryon asymmetry by spallerings. It's a beautiful way to explain the observed baryon asymmetry of the universe. However, the same scenario works for very light Majorana masses if you replace decay with oscillations. You start with, for small Majorana masses, Yukawa couplings are also small. The right-handed states are never in equilibrium, and oscillations of active neutrinos into these non-equilibrium states steal the lepton number from plasma, and then the spallerons is converted into baryon asymmetry in the usual way. So both of these scenarios work equally well. And the only question is, so it's, again, doesn't give us any clue as to what the size of the Majorana masses might be. Now, neutrinos, neutrino physics is a field where many theoretical prejudices have proven to be wrong. We thought that, people thought that neutrinos were massless. They are not. People thought that mixing angles are all small and the mass is hierarchical. Turns out that mixing angles, some of them are near maximal. So the suggestion is let's just consider any value of this parameter and see where it gets us. Dark matter. I will examine the hypothesis that dark matter is sterile neutrino, and I will then examine other ways you would produce sterile neutrinos in astrophysics, for example, in supernovae. And in supernovae, they are produced asymmetrically. They give a recoil momentum to the neutron star and explain the observed motions of pulsars. Okay, the early universe. In the early universe, for small Majorana masses, right-handed states are completely out of equilibrium at any temperature. You can produce them by off-resonant oscillations of active neutrinos. Or you may hit a resonance if the lepton asymmetry is non-zero for some unrelated reason. And people have examined both of these. You can also produce them from decays of some particle hiding in the Higgs sector, and I'll discuss that production as well. The constraints on the dark matter depend on how you produce it. KEV sterile neutrinos are not synonymous with warm dark matter. Warm or cold is a function of momentum distribution. And in these different production mechanisms, you get different momentum distributions. So we'll talk about that. The first mechanism historically people considered was just the off-resonant oscillations. And let me just take a two-state system, electron neutrino and a sterile neutrino, and with probability suppressed by sine squared theta, this oscillation produces me some out of equilibrium population of dark matter or relic sterile neutrino. The sine squared theta is not constant and it depends on temperature. And so for large temperatures, there is a huge denominator here which suppresses the mixing. When temperature reaches 100 MeV or so, you produce most of these sterile neutrinos by oscillations. And so this is a very simplistic plot which shows dark matter is okay along this red line here, and you overclose the universe here. Okay? And this is a very approximate formula for how much dark matter you produce. Since this is not thermal decoupling, since this is oscillation, the dependence on mass is quadratic, there's sine squared theta, it's a different formula, okay, from what you are used to seeing.
What happened to the thermal abundance?
The thermal abundance is zero because they are never thermally free.
No, looking if they are at sufficiently high temperature.
They would not be, because this mixing angle is suppressed at very high temperature.
They always have gravitational interaction.
They have gravitational interactions which are insufficient to bring them into. Okay, so now you may hear the lepton asymmetry. If you have some lepton asymmetry for unrelated reasons, then you may have a resonance and then you produce different amounts deviating from the straight line showed, and you also have different momentum distribution, of course, which matters for Lyman alpha bounds. Lyman alpha bounds. You can take a very remote source of light, a quasar, and look for the forest of Lyman alpha absorption lines, which tells you the distribution of small clouds of hydrogen along the line of sight. This produces the information, probably the best information we have about the small-scale structure of the universe, and we want to have dark matter which is cold enough to satisfy the bounds. But what we're comparing to the free streaming waves is not only the mass, but the average momentum of dark matter particles. The free streaming lanes corresponds to something you infer from Lyman alpha observations. It's highly non-trivial to get information from those observations, especially from the high redshift data sample of slow digital space array, where there's some unknown systematic. But once you converted it to free streaming lanes, you have to compare it to the mass and also to the average momentum. And so in the three production mechanisms that I discussed, there's factor 3 difference in what you get for the average momentum. And so the Lyman alpha bound for the production mechanism based on oscillations alone is fairly high. It tells you that the mass has to be more than 10 keV. And that seems to be inconsistent with the production mechanism, which would put you along this line. So that seems to be wrong. And I will tell you where these excluded X-rays come from. However, if you go to one of these production mechanisms, this bound moves down by a factor of 3 point something, and this whole region becomes another. Also, it's kind of amusing that dwarf spheroid galaxies, according to Jerry Gilbert and collaborators, suggest the longer free streaming lanes. I have nothing else to add, and this is something that these two groups of people will have to find out, because it's the same. This seems to be inconsistency. What I am going to discuss is, again, this Lagrangian, in which I introduce the Majorana masses. And now, suppose this is my dark matter. And suppose I chose the mass here to satisfy these constraints, so I'm here somewhere in the keV range. What is the keV? Do I mean to introduce a new fundamental scale in nature and say keV scale? Well, perhaps. Or I can get that keV scale from the Higgs mechanism, but of course I would have to couple these right-handed neutrinos to the Higgs singlet, SU2 singlet. But as soon as I do this, as soon as I touch this piece in the Lagrangian, I immediately alter the whole cosmology, because now there's a new production mechanism. These S Higgs singlet will be in equilibrium, and the keys OS in the out of equilibrium ends will produce some population of right-handed neutrinos. So now I have to compare this to whatever I get from oscillations and see who wins, and see what kind of dark matter I get and how cold it is. So what happens in that case, you get the right abundance for the Yukawa coupling 10 to minus 8 if the expectation value of the singlet is the same as the mass. And then you ask, okay, to get a few keV with this Yukawa coupling, where does the expectation value of the singlet have to be? And it turns out to be smack at the electroweak scale. So this singlet Higgs is living right where the doublet is supposed to be living, and they may be friends. Okay? Now, more importantly, here in this production mechanism, you generate the population of sterile neutrinos at the temperature of order of the electroweak scale. And then just the standard model cooling with the reduction in degrees of freedom cools down the population of sterile neutrinos. So you have entropy production in the plasma, but right-handed neutrinos are just sitting there and looking around. And so their momenta get richer by a factor close to, actually in excess of 3. And so the Lyman alpha bound from 10 keV moves down to 2.7 keV here. And so now you have this interesting range allowed. And in particular, note that this psi-n range, which I will discuss in a moment. It also is interesting what you get in this electroweak phase transition, because now you have a singlet mixed with a doublet, and the transition is different. And you also have different Higgs phenomenology, because this predicts invisible Higgs decay channels. And people have discussed that. Now to that psi-n region. There is a very interesting thing that happens in the supernova in the presence of these right-handed neutrinos. They are light enough to be produced in the supernova, so we have to examine their production. See that they don't overcool the supernova, and maybe they will do something else. And they do, in fact, do something else. They generate asymmetries and produce velocities of neutron stars that emerge from supernova explosion. They also, well, I'll talk about other predictions as well. So the pulsar velocities. If you go out tonight, the sky is clear, and you will see the stars in the same places where you saw them last night. But the pulsars will all have moved. Pulsars move with large velocities. 15% of them move faster than 1,000 kilometers per second. It's the escape velocity from the galaxy. You're never coming back. This is a picture of a very rapidly moving pulsar, which plows through a cloud of gas, hence creating this guitar nebula. And you can actually see how the position has shifted between 1994 and 2001. This is not how most velocities are measured, but this is one of the spectacular examples. They are measured with the radio telescopes. This is a map of pulsars with their velocity directions and magnitudes. And of course, you want to explain these velocities. And a number of explanations have been put forth. We can go over them in the question if you're interested. But the problem is none of them work. None of them can explain large enough velocities. And this is the results of numerical simulations by Chris Fryer at Los Alamos on the supercomputers that Los Alamos lets them use. So this is the, he examines the core collapse supernova and the velocity of the pulsar that you can get, and he concludes that 200 kilometers per second is tolerable. 1,000 kilometers per second is beyond the reach. However, what is the problem? The problem is most of the energy, 10 to the 53 Earth, escapes in neutrinos. And what is left for the hydrodynamics to work with is only 1% of energy. That's not enough to give the pulsar such a huge speed. However, if you had only 1% anisotropy in the distribution of neutrinos, you could give that momentum to the neutron star. So you have to have small asymmetry in the large pool of energy, or a large asymmetry in the small pool of energy. Okay? So let me examine this possibility. What can cause the asymmetry? An obvious suspect is magnetic field. It's very strong and anisotropic in the neutron star. And what happens in the neutron star? Well, you form a neutron star where an ordinary star collapses and produces, it generates a core which can no longer support its own gravity with pressure, and then it just collapses. And so it collapses, and you form proto-neutron star, which is very fast, or very, very hot. There's this initial burst of neutrinos, which is irrelevant, and then over the next 10-15 seconds, most of the neutrinos come out as thermal. How do you produce neutrinos? In Urca processes, you generate neutrinos in interactions of ordinary neutrons and protons and electrons in the hot neutron star. If you just consider these reactions in the magnetic field, and take into account the fact that the electrons are polarized in the magnetic field, you'll get a huge asymmetry in neutrino production. Look, you have the difference between the probability to produce neutrino along the spin and the opposite direction is 0.4 times the fraction of electrons in the lowest Landau level, and which by itself can be 0.3, 0.4 very easily. And so here you have 0.4 times 0.4, that's 15% asymmetry. You only need 1% asymmetry. Are we done? Is this the explanation of the pulsar case? Well, the reason is this doesn't work. It's the same for cosmologists. You explain by analogy with stars. Okay? You generate this asymmetry, but neutrinos have to diffuse in approximate thermal equilibrium, and the asymmetry washes out. Okay? You need a departure from thermal equilibrium for that asymmetry to survive. The scatterings of these neutrinos in hot nuclear matter wash out this asymmetry. Now, the washout of this asymmetry, well, you can also think of it, I mean, we made it a theory, but it's very easy to understand. If you take one molecule of nitrogen and drop it here, it will go down, because there is an anisotropy because of the field of gravity. But in equilibrium, there is no microscopic flux that develops in downward direction, because even asymmetric scattering amplitudes in equilibrium don't give you microscopic asymmetry. So that's the point. However, if you have a sterile neutrino produced in the same processes with some suppressed cross-section, suppressed by sin squared theta, then it doesn't have to be rescattered. It just goes out with the emission asymmetry equal production asymmetry. And then you can have a stronger momentum in one direction than another. And if you look for a range of parameters in which the asymmetry is 1%, then you end up with this purple region here, right next to the dark matter region. It overlaps the dark matter region. Kind of amusing. Now, you may also hit the resonance inside the neutron star. And the resonance position is affected by magnetic field because neutrinos don't know about the magnetic field, but the electrons do. And for the MSW resonance, the position of the resonance, the matter potential, is just the forward scattering amplitude. And you know that forward scattering amplitudes know about the orientation of the spin. And so there is this term here. So if you consider the resonance, then the positions of the resonance are altered in the magnetic field, and you get hotter neutrinos from higher temperature regions in one direction than in the other, and you get another piece of parameter space allowed for the kicks. So altogether, from taking into account all possible oscillations, you get this region here, where you explain the velocities of pulsars. And more accurately on this plot, with already existing X-ray constraints, which I'm about to discuss, it's this cyan region here, and another thing sticking out here.
Where is the Gilmore's resistance here in this one?
Jerry Gilmore wants it to be at 2-3 keV, to explain the works for it. Okay, there are other predictions of the kick mechanism. Chris Farrer did the simulation on a super duper computer, and so what happens is when you move the neutron star during the explosion, you produce more convection in the frontal direction, and so then you have a jet developing. So one expects asymmetric jets with the symmetry in the direction of the neutron star, not in the opposite direction. You don't expect the correlation between magnetic field and velocity because the magnetic field you measure now, 3 million years later, is not the same as the magnetic field during the first 10 seconds. The magnetic field is growing as part of the alpha-omega dynamo mechanism. Then the neutron star cools, undergoes superconducting phase transition. The magnetic field is squeezed into flux lines, pushed to the surface. It reconnects. It does all sorts of funny things. So you don't expect today's magnetic field of the pulsar to reflect the initial magnetic field inside the neutron star. You measure it today.
The direction has not changed.
The direction is not changed. And so what you do predict is the directional correlation between the vector of omega and the vector of velocity. And some of those correlations have been observed. In fact, there's growing evidence for these correlations, which Sudhir pointed out to me yesterday, in fact, yeah. So this is kind of an interesting area to watch. How else would you know that these are the dark matter particles? Well, you have written the Lagrangian, you know everything, you can calculate the decay rates. If you take one of these heavy neutrinos through mixing, it can decay via this loop into a lighter neutrino and a photon. And since this mass is keV, this photon is half the mass. And it's a two-body decay, and you're looking for a narrow line from a collection of dark matter particles. By existing observations, just serendipitously, one can set constraints already. From non-observation of a narrow line, by, say, Chandra X-ray telescope when it was pointing at Virgo cluster, or when it was pointing at blank sky for calibration. So these decays, of course, are very slow. The lifetime is much longer than the age of the universe. But there are enough dark matter particles to produce an observable signal. But what you would want to have is some kind of a dedicated search when you point your X-ray telescope to some quiet place where there are many dark matter particles, and you look for this line. And so a very good place to point the telescope is one of the clumps of dark matter in our own galaxy, the dwarf spheroidals. For example, there's one in Ursa Minor and another one in Draco, here and here. And so these would be very good targets to point the X-ray telescope, but for a while we couldn't convince the X-ray people to take their favorite toy and point it in the darkest corner of the universe, where they don't expect to see anything. And one grand proposal that I wrote returned with the, this is great science, everything, but there is a chance of non-observation, so it cannot be funded. For astronomers, non-observation is the ultimate failure. Right? The guys set out to observe something, they didn't. Come on. Okay. So, but we finally got observing time on Suzaku X-ray telescope, which is an excellent instrument in space built by the Japanese. And we had 36 hours of observation, 18 hours for each of these dwarf spheroidals just now. And the data, we have the data, we haven't analyzed it yet. Based on what we simulated for our proposal, we should be able to explore this region here and look for a light. So we'll see what happens. There's another interesting job for these neutrinos in the early universe. The same decays that can help us discover them can play a role in star formation. See, to form stars, you need to reach a certain fraction of molecular hydrogen. This is a plot from Max's paper. And the reason is that it's only, the atomic hydrogen is not very good a cooling agent. The cloud of atomic hydrogen doesn't like to collapse because the energy levels are too widely spaced, like quantum mechanics. And so when the two atoms collide, they can't dissipate kinetic energy very efficiently. But when you have molecules, you have rotational and oscillational levels, which are very finely spaced. And so as soon as you created molecular hydrogen, gas begins to dissipate kinetic energy and can collapse and form the first stars during the dark ages. So this reaction, how do you form molecular hydrogen? This reaction is very, very slow. But if you ionize one of the H's, it goes very fast. Like in freshman physics, the charged things are charged neutrally. And so the production of, if you ionize hydrogen, that catalyzes the production of molecular hydrogen in the primordial clouds. And so we calculated the effect of decaying spiral neutrinos and the X-rays they produce on ionization of hydrogen. By themselves, they only raise ionization fraction to about 10 to the minus 2 at redshift between 50 and 100. However, in the absence of these spiral neutrinos, the ionization fraction will be 10 to the minus 4. So it's too small to show up in WMAP, of course, 1% or 1/100th of 1%. But it is 2 orders of magnitude increase in the ionization fraction, which plays a role in the formation of molecular hydrogen. And so then you see, they play a role in stuff. Now, all of these astrophysical clues, like the pulsar kits and others, they're too weak to be taken seriously individually. But there is this consensus of several independent pieces of evidence which seems to be pointing in this direction, and we feel that this creates a strong motivation for the search we're doing. And so we're searching for this with Suzaku. Later this summer we'll probably have the results. And there's also a very interesting proposal in Europe, complemented by a NASA proposal, of an X-ray telescope with very high energy resolution and wide field of view, which will do a number of marvelous things. And in addition, it will be the dream instrument for this dark matter search, if we don't see it. So let me just summarize that sterile neutrinos almost certainly exist just from the fact that we need to explain the ordinary neutrino masses. Okay, so you need the right-handed fields, and you introduce them in just about every model of neutrino mass. The only question is at which scale you put the Majorana mass. If you allow one of the Majorana masses to be at the lower energy scale, you get dark matter. You can reproduce baryon asymmetry through leptogenesis. You can explain the observed pulsar velocities. And the way to look for this form of dark matter is through its slow decays into X-rays and light neutrinos. And so this seems to be the most promising avenue for pursuit. So let me leave this slide up and we'll take the question.
Okay, we're questions. Yes.
Short question. If the neutrinos, the heavy neutrinos, have never been in thermal nucleus, the process of structural formation that you usually imagine is that there is a homogeneous background with nucleus conformation factor. And this also happens this kind of.
Yeah, it just works the same way as cold dark matter works. It's just, for all intents and purposes, as far as structure formation is concerned, it's dark matter which is cold on large scales, and then at some level on small scales, there is free streaming. However, free streaming lengths could be smaller than anything we can observe, or it can be within the range of probed by the observations of Morse coordinates. And that depends on the production mechanism, as I described. So,
what mechanism produces a homogeneous background nucleus configuration in this kind of neutrinos?
no, presumably you have inflation in the early universe, and that generates the spectrum of density perturbations. What you need for those perturbations to grow is dark matter which is cold enough. And so when the matter radiation equality occurs, okay, these perturbations look around and say, wait, okay, now we can grow if there's something that would stream into potential wells. And so the dark matter particles say, oh, we're cold enough, so they run into the potential wells, and these homogeneities start growing.
There are neutrinos of transition at any moment. Will they be converted to light neutrinos in the place of like galaxies like
With a vanishingly small probability. Unfortunately,
even in the vicinity of some strong magnetic field.
yeah, unfortunately, this is a very. It's a good question, but my back of the envelope estimate gave a very discouraging result. If it didn't make it, 40 orders of magnitude error, that's very.
I'm not sure about the numbers, but when you make a vector observation of the and you also get 40% conduction to motion average, expecting that to see.
Yeah, it depends on what you're looking for. Once we have the data, then one can ask different questions and try to answer them using these data. And the data we have collected, it's great to have X-ray data from a very X-ray quiet region dominated by dark matter. So so we can ask various questions, and the data will become public 1 year from now. So everybody is welcome to ask, various questions.
Okay, let's